topic for the lecture today is local soundness and completeness. Local soundness and local completeness. So we have developed this system of inference rules based on the natural deduction style. And there are many elimination rules. Given an introduction rule, we have designed these elimination rules. And the question now is, what is the guiding principle about whether we should accept these inference rules, in particular elimination rules? For example, this introduction rule appears to make sense because it just states what our intuition tells us about the meaning of conjunction and. But what about these elimination rules? We'd like to develop some kind of criterion so that we can test if these elimination rules are indeed okay, or if there is some sort of a bug in the design of these elimination rules. So we'd like to test the two properties called local soundness and local completeness against this system of inference rules. Let's first review the interpretation of introduction rules and elimination rules in terms of knowledge expressed in the judgment. So here we have an introduction rule. Introduction rule, in some sense, so let's just say we have this A conjunction B true. So we have this premise. In some sense, this introduction rule compresses the knowledge expressed in the premise, so this is some form of knowledge, into this single judgment. This is introduction rule. In the case of an elimination rule, the opposite occurs. Say we have this judgment and we apply this elimination rule. And what happens is we retrieve the information compressed into this single judgment. We now retrieve. So here in the case of conjunction introduction rule, we compress the knowledge expressed in the premise into a single truth judgment. In the case of elimination rule, we start with this single truth judgment and we retrieve some knowledge that is justifiable by this truth judgment. So we can interpret this introduction rule, elimination rule in terms of knowledge. Knowledge conveyed by the judgment in the premise and in the conclusion. Then what is the local soundness property? The local soundness property states that, let's say we have some elimination rule, say A conjunction B true, and by applying this elimination rule, we retrieve some knowledge. Okay, we retrieve. And local soundness property says that this new knowledge extracted from this truth judgment by this elimination rule should be sound. This thing should be sound. Or it should be part of the original knowledge that we used to construct A conjunction B true, this truth judgment. So in other words, we compressed this amount of knowledge by applying introduction rule, and we have this single truth judgment. And whatever comes out of this elimination rule, this thing must be justifiable with respect to the original knowledge that we started with. So intuitively, this new judgment or this new knowledge should be part of this original knowledge. A better way to understand the notion of local completeness is to see what would happen if this local soundness property fails. Let's say we start with this amount of knowledge, and then we apply introduction rule, let's say conjunction introduction rule, and obtain a single truth judgment. Now we apply elimination rule and retrieve new knowledge. So intuitively, this new knowledge should be part of, or it should be included by the original knowledge that we started with. But if the local soundness property fails, what would happen is, by applying this elimination rule, we obtain some new knowledge that cannot be justified by this original knowledge. In other words, by applying this elimination rule, we produce or we contrive some new piece of knowledge that is never justifiable according to the original knowledge that we started with. So if this local soundness property fails, what that means is that by applying the elimination rule, we can contrive some new judgment like this one. But that means that the elimination rule is too strong, because this elimination rule allows us to generate some new judgment that is completely unrelated to the original knowledge that we started with. So this knowledge has been compressed into this single truth judgment. And by applying this elimination rule, we can suddenly generate something new, some new knowledge, completely out of the blue. So this is not acceptable. So local soundness property states that this does not happen, or elimination rule is not too strong. So local soundness says elimination rule is not too strong. So intuitively, local soundness property says that if you started with this amount of knowledge to generate, say, a conjunction be true by applying introduction rule, no matter how many times you apply elimination rule in what sequence, the sequence of applying this elimination doesn't matter. So no matter how hard you try, what you get is only part of the original knowledge. You never generate something completely new. This is never generated. So intuitively, this new judgment generated by this elimination rule is sound, or it makes sense. On the other hand, this new knowledge that lies outside of the original knowledge would be unsound, or does not make sense. So to summarize, local soundness property says that the new judgment that you obtain by applying the elimination rule is a sound in some sense. And what that means is that this is going to be part of the original knowledge. And if local soundness fails, you can generate something completely unrelated to the original knowledge. So that would mean that elimination rule is too strong. So that's what the local soundness property is about. Now let's discuss local completeness. Local completeness means that by applying elimination rule, by applying elimination rule, you can generate a new knowledge. And local completeness means that if you combine all these new judgments that you can generate by applying elimination rule, you can reconstruct the original knowledge that you started with. So here's an example. Suppose that you start with this amount of knowledge, and then you apply introduction rule, okay? And then you generate, say, it's a single truth judgment. And now you apply elimination rule as many times as you like, or in whatever sequence you like, and you generate new judgments. And if you combine all these new judgments, the combined sum of these new judgments should include the original knowledge that you started with, or at least include at least. Then what happens if local completeness fails? If local completeness fails, say local completeness fails, what happens is that you started with this amount of knowledge to construct A conjunction B true. And no matter how hard you try by applying conjunction elimination rule, okay, you retrieve new judgment, but you never reconstruct this new knowledge, the original knowledge that you started with. So if local completeness fails, you miss something that was part of this original knowledge. So in other words, you fail to reconstruct the original knowledge once you apply this introduction rule. So in some sense, we can say that the elimination rules are not strong enough, because once you apply this introduction rule, you never get back what you started with. So for example, you started with, say, information worth $100. Okay, so this single judgment is worth $100 supposedly, but because of the bugs in the design of these elimination rules, now no matter how hard you try, you only get back information worth, say, $50 only. So there's something wrong with these elimination rules, because no matter how hard you try, you never get back what you started with. So in that sense, we can say that elimination rules are not strong enough. So to summarize, local completeness says the elimination rules are strong enough. You never lose anything. And if local completeness fails, once you apply this introduction rule, there's no going back. You can never rebuild the information that you started with. So say if this conjunction elimination rule was not strong enough, then we would never get back this information worth $100. Every time you apply this conjunction introduction rule, you lose something, because you can never reconstruct part of what you started with. Okay, this is the notion of local completeness. And what happens if both local soundness and local completeness holds? If these two properties hold, then say you start with this amount of knowledge, and then you compress this knowledge into a single judgment, let's say A conjunction B true. And thanks to the local soundness, all these new judgments that you obtain by applying elimination rule, this is an introduction rule, by elimination rule, these new judgments are all sound. They are part of this original knowledge. And thanks to the local completeness, if you try hard enough, then you can reconstruct the original knowledge that you started with. So now, if both local soundness and completeness holds, then you can apply this introduction rule without worrying about losing information afterwards. Because by applying this elimination rule, you can always retrieve the original information here. So if you apply this elimination rule sufficiently many times, you can retrieve precisely the same information that was compressed into this introduction rule. So that's the notion of local soundness and local completeness. Now, we'd like to check if this system indeed satisfies local soundness and local completeness. Let's first investigate how to verify local soundness and then local completeness. So how do we check local soundness? Remember that local soundness means if you start with this information, then after apply introduction rule and then apply elimination rule again, whatever comes out of this elimination rule should be part of the original information. Okay, so it is a sound. It is not something unexpected. If you generated something that lies outside the original information here, then this would be unsound because there is no way to justify this new judgment. So how do we check local soundness property? We show how to reduce a proof where an introduction is immediately followed by the elimination rule. So in other words, we have this proof, we have a proof, say conjunction introduction is immediately followed by conjunction elimination rule, and then we show how to reduce this proof without applying this intro and elim rule. So here's an example. Let's say we apply conjunction introduction rule to deduce A conjunction B true. So we have A true here and B true here. And suppose that this conjunction introduction rule is followed by one of the corresponding elimination rules right away. Let's say conjunction elimination rule left. Then we have A true here. In some sense, we take a detour here. Detour. We'd like to prove A true, and we apply this conjunction introduction rule for some reason. We introduce this conjunction. We introduce a conjunction here, only to find that it is eliminated right away. Then we might ask ourselves, what's the point of applying this conjunction introduction rule? Because it's going to be eliminated anyway. So it looks like we are taking detour here. Suppose that we have a derivation tree like this one, and the question is, can we reduce this derivation tree into another one deducing the same judgment, but without taking this detour? And in this particular case, it's pretty easy to see because we just take this sub derivation tree, that is, we make a copy of this smaller derivation tree, and then we deduce A true directly. Here, we take this detour because intuitively, there's no point in applying conjunction introduction rule only to eliminate it right away. Instead, we could just take this direct path to prove A true. Why is it that by showing a derivation tree of this form is reducible to a more direct proof? Why is it that this is sufficient to show the local soundness property? The idea is like this one. You start with this one, this knowledge, and then you apply introduction rule, let's say conjunction introduction rule. And suppose that you apply conjunction elimination rule right away. If local soundness property holds, then this should be part of the original knowledge. Therefore, we should be able to extract this one right away without taking this detour. So that is, the question is, can we reduce this derivation tree without taking this detour? To summarize, to show the local soundness property, take a derivation tree of this form, some introduction rule immediately followed by some elimination rule, and then show that the same judgment can be proven without taking this detour. Here we don't have intro followed by elim. So this is how we verify local soundness property. And how do we check the local completeness property? Local completeness. So how do we check this local completeness property? And here we take precisely the opposite approach. This time, we start with a derivation tree involving a particular connective. For example, A conjunction B true. And we apply elimination rules as many times as you like, in whatever order you like. So in other words, we apply these elimination rules to extract as much information as we can out of this A conjunction B true. And then you apply corresponding introduction rule in order to rebuild the same judgment. So the idea goes like this one. Suppose that you start with this amount of information, and then this information has been compressed into A conjunction B true. And if these elimination rules are strong enough, then by applying these elimination rules, we should be able to retrieve all these, the entire information that we started with, if these elimination rules are strong enough. Suppose that these elimination rules are strong enough, and we can perhaps retrieve the original information. Then how do we test? How can you test if we have indeed reconstructed the original information? If we managed to reconstruct the original information by applying this elimination rule, we essentially have precisely the same amount of knowledge. Therefore, we should be able to deduce A conjunction B true again by applying introduction rule. And this would be not possible if elimination rules were not strong enough. For example, no matter how hard to try, we never retrieve this judgment, this part of the information. Then this part is missing, so therefore we would not be able to reconstruct A conjunction B true. So to summarize, to show that a particular connective satisfies local completeness property, start with a derivation tree, a proof like this one, and then apply elimination rule and collect as much information as you can, and then finally show that by applying the introduction rule, you can prove precisely the same judgment. In this way, we can indirectly show that all these elimination rules are strong enough that we can we can retrieve the original information here. So here's an example. Let's say we have A conjunction B true. How do we reconstruct A conjunction B true after applying elimination rule? First of all, let's try to obtain as much information as possible by elimination rule to this judgment. So for example, we can apply conjunction elimination rule left rule. So we have A true. We can replicate this derivation tree. So make a copy of this derivation tree here. And there's another way to apply elimination rule, conjunction elimination rule, right rule, and we have B true. So it turns out that these are the only ways to apply elimination rule. Now you collected this proof of A true and B true. And by applying conjunction introduction rule, you can rebuild the proof of the same judgment. So we expanded the derivation tree. This time, we expanded the derivation tree by taking this detour in some sense. So this conjunction satisfies the local completeness property because we have shown that by applying this elimination rule, we essentially retrieved the original information without losing any part of it. And how do we verify that we have retrieved the original information in its entirety? We show that by applying this conjunction introduction rule, we rebuild the same judgment. Okay, so this is the way that we check local completeness property. Now let's see two more examples using this implication. Let's test the local soundness property. Remember that local soundness property is all about introduction rule immediately followed by the elimination rule. And if we have this form of derivation tree, can we reduce this derivation tree deducing the same judgment without taking this detour? So we deduce the same stuff, but this time we don't take this detour. So we start with a derivation tree of this form. So let's look at an example involving this implication. So we first have to have this introduction rule, implication introduction rule. So A implies B true. We introduce hypothesis A true. Let's just say this is X. And then we use B true. This is the implication introduction rule. And the assumption here is that this implication introduction rule is immediately followed by the corresponding elimination rule, this implication elimination rule. And in order to apply implication elimination rule, you have to have a separate proof of A true. Let's call it D, and then you deduce the B true. So now we will have a proof of B true, and the question is, can we reduce this derivation tree, this proof, into something smaller, deducing the same judgment, but this time without taking this detour, intro followed by elim. And the idea is actually quite simple. We have a proof of a B true, but not complete the proof. We almost have a proof of B true if you allow the use of this hypothesis. So you make a copy of this one here. Okay. Of course, this is not a proof of B true because it includes this hypothesis. Now the goal is to get rid of this hypothesis. And the idea is we just we substitute this proof of A true. This proof is complete because it doesn't depend on any hypothesis. So you make a copy of this one over here, and then this hypothesis disappears. in reality, you have to actually make copies of this proof many times. Actually, as many times as there are these hypotheses inside this derivation tree. So, for example, if you have 2 copies of this hypothesis, remember that when you apply this implication introduction rule, you may actually use the hypothesis just once or twice or 0 times or as many times as you like. So you have to make copy of this derivation tree D just as many times. Okay, so in fact, in reality, you might have something like this. But the point is, you make a copy of this partial derivation tree and then replace this hypothesis with this complete proof of A true. Now you deduce the same judgment to be true without relying on this detour intro followed by elim. So we reduce the derivation tree. And the conclusion is implication connect the elimination rules for this implication connective satisfy this local soundness property. And what about local completeness property? Remember that for checking local completeness property, you start with an existing derivation tree involving the particular connective of interest. So you have A implies B true. A proof of A implies B true. The question is, can we expand this time? This time we have to expand by first apply elimination rule so that we can collect as much information as possible from this judgment. And then you apply introduction rule to see if you can rebuild a proof of the same judgment. So the pattern is first apply the elimination rule and then introduction rule. So let's apply. So we have A implies B true, D, and perhaps you will apply implication elimination rule, and then you will apply implication introduction rule to deduce the same judgment. The question now is, can we complete the proof by filling in this missing part? And it's pretty easy. By applying implication introduction rule to this judgment, your goal reduced to proving B true with the new hypothesis A true. Let's say this is X. And then it's just a matter of applying this implication elimination rule. Combine this one, and you can complete the proof of B true. So again here, you apply an elimination rule first, and then apply introduction rule to rebuild the same proof essentially. So implication satisfies local completeness. In similar way, you can show that disjunction satisfies local soundness and local completeness. So to summarize, how do we check local soundness? We'll start with a proof or derivation tree where some introduction rule is immediately followed by elimination rule. It's a conjunction introduction, conjunction elimination rule. And then show that you can deduce the same judgment without taking this detour. So because this detour is eliminated, we reduce the derivation tree. We reduce this derivation tree in terms of complexity, not actually in terms of the size, because you may actually make copies of hypotheses. So when you actually perform the substitution, this derivation tree may grow in size but it always reduces in terms of complexity. So we say that this derivation tree locally reduces. So we call this reduction local reduction. In this way, we can verify if a pair of introduction and elimination rule satisfies local soundness. What about local completeness? At this time, you start with a proof that involves a particular logical connective, and then try to expand this time by first applying elimination rule as many times as necessary, and then apply introduction rule to deduce the same judgment. So the derivation tree increases in complexity, so we call this expansion local expansion. Finally, let's discuss top and bottom. Top and bottom. There's no local reduction because in order to show local soundness or local reduction, you have to have introduction rule and an elimination rule. But these logical connectives, top and bottom, don't have both local, introduction and elimination rule. Either introduction rule is missing. In this case, elimination rule is missing. And in the case of bottom, there's no introduction rule. So therefore, we cannot talk about local soundness simply because we can never build this detour of the form intro followed by elim. So there's no notion of local soundness. But it turns out that we can actually establish local completeness. So here's an example. Suppose that we have a proof of top true. Suppose that we have a proof of a top true. How can we expand it? Well, you just apply introduction rule. Remember that here, you apply the elimination rule as many times as you like so that you can collect as much information as you want. But it's just optional. You may choose not to apply elimination rule. That's acceptable. So in this case, we choose not to apply elimination rule simply because there's no elimination rule. So you just apply introduction rule and then obtain this derivation tree. And what about bottom? Well, bottom, if you have a bottom true, then you can deduce any judgment. So remember, the bottom elimination rule looks like this. Apply bottom true, and then you can deduce anything. And C can be anything, including bottom itself. So by applying bottom elimination rule, you automatically obtain this bottom. So for the top and bottom, we can talk about local completeness, although we cannot talk about local soundness.